Hello! Today I'm going to be walking you through my final project for ENME489Y, remote sensing. The goal of this project was to create a 3D point cloud of an on-campus target using a build-it-yourself LiDAR system. The motivation behind this class is to get hands-on experience with LiDAR, which stands for Light Detection and Ranging, and to understand the applications of the technology, like self-driving cars, mapping the Earth, or even assisting in emergency operations. LiDAR is similar to radar, which stands for radio detection and ranging, but it uses a higher frequency of light. As such, LiDAR is capable of creating incredibly detailed point clouds. In this video, I'm going to show you how I used a LiDAR to create a 3D point cloud of the Testudo statue in front of McKeldin Library. I chose Testudo as my target because of his significance to the UMD community. His nose is shiny from being pet by students, and the rest of his body is matte black. And sometimes he is covered in offerings from students who need some extra luck to get through finals. In addition, I thought that his simple rectangular base would make it easier to align my 4 point clouds later on. Although Testudo poses unique challenges, namely his complex geometry and the abundance of offerings surrounding him, I thought mapping him would be a great way to commemorate my 4 years at the University of Maryland. Remote sensing is the ability to collect data from a target without physical contact. This technology allows us to collect data in places that are inaccessible to humans or dangerous. Some remote sensing applications include satellites, other aircraft-based systems, and self-driving cars. It is typically split into 2 categories: active sensing, when a signal is emitted, reflected, then received, and passive sensing, when the system does not emit a signal, but rather it detects sunlight. My LiDAR is active because it emits red laser light, but a regular old camera is a great example of a passive system. If the flash is off, the camera just detects ambient light from the sun that is reflected off of the target. LiDAR is an example of active remote sensing. As such, 2 key elements are the transmitter and the receiver. Generally, the LiDAR emits a laser pulse from the transmitter and detects the return with a receiver. The time it takes for a pulse to return to the receiver, along with the speed of light, is used to calculate the distance of a target. In my system, the transmitter is the red 5-volt line laser, and the receiver is an 8-megapixel Pi camera. One of the biggest differences between my system and many real-world LiDAR systems is the large distance between these 2 components. My laser and camera are separated by 12 inches, mounted with screws and glued with epoxy to my chassis. Additionally, my LiDAR operates at just one wavelength, 650 nanometers. Many LiDARs that are used to map the planet operate in multiple bandwidths to get different types of data from a single scan. In order to begin the data collection process, I had to calibrate my system to account for the relative alignment of my camera and my line laser. To accomplish this, I performed calibrations with a single beam laser, then with a line laser. To calibrate the single beam LiDAR, I took photos of the projection of the laser on my wall at distances ranging from 10 to 0 feet. As the LiDAR moved closer to the target, my wall, the laser spot moved farther away from the center of the image. I plotted these data points against a theoretical curve, which is based on the geometry of the system. Then, to calibrate the line laser LiDAR, I followed a similar procedure. With the added degrees of freedom of a line laser, I needed to tune 2 parameters, ρ and RPC, to make the points fit the curve, thus calibrating the system. For both calibration exercises, I used OpenCV and Python on my Raspberry Pi to take images, plot crosshairs, and locate the laser with respect to the center line of the image. After my system was calibrated, I went to my target, Testudo, to begin data collection. I decided to take separate data sets from 4 sides of Testudo, normal to each face of the concrete base. On each side, I took about 30 photos since I wanted my point cloud to be as dense as possible. I took each photo by running a script on my Raspberry Pi that prompted for an angle, as measured by my phone, took a long exposure photo, plotted crosshairs, and saved the photo on the Pi. After repeating this upwards of 100 times, I transferred the files using Google Drive and proceeded to my laptop for processing. One of the biggest challenges I faced was wind. I would often have to hold the camera steady when there was a gust. Because of the 12 inches of separation between the laser and the camera acted as if it were on a cantilever beam, creating blurry long exposure photos. Holding the camera still by hand solved this issue. Additionally, outside lights caused camera oversaturation, particularly when taking data on the right side of Testudo. To mediate this, I physically stood between my target and the outside light sources, removing any erroneous data points later on. This helped me get a more detailed scan of the top of Testudo. The first step in my processing was to convert each photo to a set of points. In order to achieve this, I used a Python script called Color Picker to determine HSV values for each image that would block all signals except for the red line laser. Because of the varying background light, I had to create about 3 different HSV filters for each of the 4 sides, so 12 HSV masks in total. Using these values, I put the images through a script that converts the filtered images to points using geometry and the calibration parameters from earlier. Next, I took these XYZ data points and moved them over to MATLAB for further processing. First, I did some manual filtering on each dataset. Then, I used the MATLAB outlier function to remove some more noise. Next, I rotated each set to 0, 90, 180, and 270 degrees using rotation matrices. Then, starting with the front dataset, I added in each additional dataset and shifted it into place with respect to the others by translating along the X and Y axes. The result is a full 3D point cloud of Testudo. My point cloud is a pretty good representation of Testudo. The points have similar dimensions and proportions as the real statue. The one downfall of my dataset is the hole in the top of Testudo. This is due to the low height of my camera. However, it was a trade-off. When I had my camera positioned higher, I couldn't get a very dense point cloud due to the limited resolution of my angle measurement app. After creating my final point cloud in MATLAB, I went to MeshLab to create a 3D printable mesh. To start, I thinned out my point cloud by deleting every third point from the dataset. Then I computed the normals and tinkered with the parameters for a Poisson surface reconstruction. Although I did not generate a very accurate mesh, I think I can attribute it to the gaping hole in the top of Testudo, as well as the error that I was unable to remove from the point cloud. Overall, this project was engaging, challenging, and educational. I now understand basic LiDAR systems, and I have a 3D point cloud of Testudo to show for it. I hope you enjoyed this video. Thank you so much for watching.